Greetings, dear friends, fellow programmers, and those aspiring to be. I hope you've been following along on this journey about closures in JavaScript, because if you did, right now I'm sure you're already familiar with concepts like modules and function factories and things of those sorts. And today we will be extending your knowledge by introducing memoization. Now, what this is an extremely powerful caching mechanism that is going to allow us to utilize closures in order to basically remember the results we were receiving from some very tough calculations that require a lot of time and resources in order to be executed. So, when you do not want to repeatedly invest the same time and efforts to do the calculations, you can use this pattern to remember the results you got when you used certain attribute values. So we will be remembering for which particular attributes we get which results. And that way, when we get the same attributes that we already used to calculate the result, we will just spit out the result we already got previous time, because the result is going to be the same. So, this is a very simple yet powerful caching mechanism that you can build in JavaScript by just knowing and understanding closures properly. So, let's jump right into the actual implementation. But before we jump into our IDE and start actually tackling this implementation, I would like to remind you that closures are a really powerful mechanism that will skyrocket your JavaScript experience and understanding if you master it completely. So, if you did not follow along on this journey of mastering closures, I would like to kindly invite you to do that, because that is the only way you will be able to get the most out of this video, because today we are working with a more advanced concepts, and I will basically take it for granted that you already are familiar with some of the basics about closures. And now, let me show you how to implement memoization in JavaScript. And welcome to our IDE environment. And before we begin with the actual implementation of memoization and how the concept works, let me tell you what we have here when it comes to code. So, the first thing we have is a very slow function. I want you to be very creative and imagine the scenario that this function is crunching some heavy numbers, reading some huge files, doing something very complex that will require a lot of time and efforts for JavaScript to perform. And we want to cache the results we get from this function. In our case, that's not going to be complex. We're just going to store the number that we provided as a parameter times 2. But that is why we need some imagination. And also what we have is our memoize function, which is going to have a single variable called cache, which is where we will be storing our cached values, and it is going to be a dictionary of sorts. So it will have key value pairs, where the key is going to be the set of arguments we provide to the function, and the value of that dictionary is going to be basically the result we got from executing slow function with arguments we provided. So let us investigate the code of the memoization function itself. What we have here is first a set of arguments, and we first stringify it using JSON library included in JavaScript. And then we check whether we have a result in our cache local variable that has a key provided as an argument here. And if it does exist, then we will just indicate using console log that we found a result, and we will not have to execute the slow running function. And we basically just return the value we found. On the other hand, if we did not find any results with the key we provided, we will then execute the slow function, which is going to calculate the result for us, store it in this variable, and then we just push the value of this result into our dictionary, where the key is going to be the set of arguments we passed to this memoization function. Basically, after that, we just return the result. So, let us see how this works in action. What we are doing here is we are instantiating two different instances for memoization function. We have created two different separate closures, and each of those closures will have its own memory space. And both of them will be using slow function as a function that is going to be used. So let us start executing these functions and see what happens. What do we have here? We first have for argument 5, we have result 10 with slow execution. So this is the first execution. We still have no cached results in our cache variable, so we have to run the slow function. But for the second time, we use the same closure instance for memoization and we pass the same argument. We will receive cached value result, not having to call the slow function to get the response. So we will receive results much quicker because we are just fetching it from memory and we already have the result. But when we invoke the same closure with a different argument, which we have not cached previously, we are again invoking the slow execution function. So we are storing the value, and again after that, as many times as we like when we invoke this, we will get the cached value because we already know what is going to be the result. But one more slight thing I want to mention is when we are using the second closure, so the second fast function, which has its own memory space, and we pass the same argument that we already used with the first closure, we will again have to run slow function. So the fact that the argument is the same means nothing when you are looking at the different memory space for cached results, meaning that this part right here has only single cached value, which is for argument 10. Basically, all of these situations that we ran before mean for nothing because they are working with a different memory. And now I would like to share a personal story of mine and how understanding closures and utilizing memoization pattern allowed me to land a job in an amazing company where the competition was really tough, and I managed to land the job out of almost 1,000 other applicants. So let me share a bit of a backstory. So first, the job required 5 different stages of interviews. The first 2 being English and also social skills and HR discussion, like regular story. And the third stage was basically going to be a live coding test. So I had an interviewer who is going to see what I'm doing. I'm sharing my screen, he can see what I'm doing, and I'm doing an online discussion where I was supposed to implement Fibonacci sequence calculator. If you do not know what that is, you basically pass a number and it returns the following result. If we pass 5, it will return a result which is going to be equal to 5 times 4 times 3 times 2 times 1. So if you pass 10, it will be 10 times 9 times 8 and so on. So basically, that was the task I received. But what was interesting is the fact that they already gave me a working solution that was using for loops, and they asked me to improve it and make it work better and to do it as well as I can. My initial approach was from my computer science learnings. I knew that I could use recursive approach to do the same, because you can invoke the same function inside of the same function to calculate the value that you want for that. I knew that improved version of that solution was going to utilize recursive calculation. And when I implemented this recursive solution, it was still very simple. It still had only a couple of lines of code, and it did show that I understood how to utilize recursive coding, but I was still sure that the solution I provided was not going to be good enough. So I started thinking about potential ways to improve it even further. And that is when I figured that closures are remembering their state, and I'm constantly repeating the same executions over and over again. So even though at the moment I did not know about memoization pattern, I knew and understood closures. So what I wanted to do was to store the states of calculations of previous calculations into the variable stored in a closure, so next time I needed to calculate something, I would not have to calculate it again, I could just use the already calculated result. So what I did was initially I had this result for the recursive solution for this problem. And basically what we are doing, we're receiving n and checking whether n is less than 1. If it is, we return n, because that's it, we reach the end. And if not, then we are returning the multiplication for n minus 1 plus n minus 2 for Fibonacci sequence. So we are recursively calling the same function from itself. And as I said, I figured this solution relatively easily. But then I wanted to improve it. That is when I started utilizing my closure understanding and tried to save the states. Okay, now let me show you why this is not the best solution and why it needs substantial improvement in order to be great. So when we run this code, you'll see that it takes almost 800 milliseconds for this method right here to calculate Fibonacci sequence for number 40. So it's like 40 times 39 times 38 times 37 and so on until 1. So it takes 800 milliseconds to do this calculation. I knew I needed to improve the situation a lot. And what I did was the following. I started brainstorming and I started saving the final result I got as a result of this calculation. So I would basically do what memoization does. Right here, I'm creating memoized Fibonacci instance, which is going to be our already existing memoize function we used in the first example, but we are just sending Fibonacci method instead of slow process method that we create. The implementation is still the same. So what I'm doing right here, I'm timing how long it takes this method to execute, as I did in the example without memoization, and I'm basically displaying the result and time it takes to execute it. So let us run this and see what is going to be the result. What we have here, this right here is the solution we had before, like 800 milliseconds. And it is without memoization included. Now, when I run this right here, which is memoized result, we again have similar results. We get around 800 millisecond result time. And that is no improvement whatsoever. But we can see that we have cached the result, and the next time when I run it with the same exact attribute, I immediately get the response. So in 0.1 millisecond, I get the response. 8,000 times faster. That is this scenario right here. But when I invoke it with a different argument, we get the same issue. We again run everything from scratch. And the execution time for 42 is going to be 2 seconds, which is huge amount of time. And it is just 42. Imagine putting in 100. It would take years to calculate. So what I wanted to do in my coding example was to cache every single result we calculated. So if I entered 40, I would log the result for 40, for 39, for 38, for 37, and so on until 1. And then when I invoke 42, I would just pull out 40 that was stored in cache, multiplied by 41, and then multiplied by 42, and I would return the result. And then store the results of those immediate results. And then just basically store the values we had to introduce in between, so between 40 and 42. And what the implementation is going to look like now is something like this. Let me show you. So here is our new implementation for Fibonacci sequence. What we have here is, again, very similar implementation as the one we had before. We are still checking whether n is less than 1 and we are just returning n, and if it is not, we are passing n minus 1 and n minus 2, but this time we are using memoized Fibonacci improved result. So we are using memoized function for calculating, which is going to store all the in-between values while calculating Fibonacci sequence. So when we run this piece of code, we will get the following results. As you can see here, we have cached all the values between 1 and 40. So we have first results between 1 and 40 put into cache. So when we run it first time now, it takes 6.5 milliseconds instead of 800 as we had in the first scenario. That is because we are just putting in our cache values, which we then pull out when we need them. So we do not have to perform nearly as much calculation as we had to before. But the main advantage is going to be when we invoke number 42. Because for number 42, we already have 40 out of 42 results stored in cache. So we just pull out the result of 40 and we just add results for 42 and 41. And we store them in cache. And the result takes 0.3 milliseconds when compared to 2 seconds it took in the previous example. I hope you understand what are the benefits of using this pattern. It's insane how much performance boost you can create with it. But you have to be very careful while utilizing it because you can easily run out of memory because you are storing so much data in your memory that you can break stuff with that fact. This is insanely powerful mechanism, but you have to be using it very carefully. So basically what I wanted to achieve here was to share my personal experience and my personal benefit I had from understanding closures. I hope you enjoyed the video, and if you did, I would like to kindly invite you to subscribe to the channel so you never miss another lesson like this one where I'll be sharing my personal experiences and the benefits you will have from mastering them. So I would like to thank you for watching and as usual, wish you happy coding!